Hi, I'm Jim Heffron. These are my lessons on Calculus 1. Okay, so we're about to start in. We're going to get through Chapter 2, which is the definition of limit, the very important definition of limit. And so today we want to motivate the definition of limit. We want to talk about why it is that you want to go through this process of getting closer and closer to some anchor point. Okay, very good. Let's get started. Okay, so let's see. There we go. So if you're given a function and a point, we want to know how the function changes near that point. Calculus is the language of change, so we're starting in on figuring out how do you compute the change. The most familiar case of understanding how a function changes is when you have a function whose graph is a line. If you plot the input on the horizontal axis, the x-axis people usually call it, and the output on the vertical axis, then the slope compares the change in input to the change in output. So of course here's the familiar slope formula. Delta y over delta x. And that tells you how the change in x is related to the change in y. So we want to develop on that idea. I wrote down a number of slopes here just to give a person some idea. The slopes go all the way, you can see, from 1/4 to 3. And the major lesson that I want a person to walk away from here is that even if you look at a slope that is as little as 1/4, it's still 14 degrees. It would be tough to walk up that slope. I mean, you'd be breathing hard after not all that long. By the time you get out to a slope of 3, and 3 is not a very big number, by the time you get out to a slope of 3, you really, you couldn't walk up that. If that was like a riverbank, you'd have to be like scrambling up and grabbing, logs along the way kind of thing. So slopes, although the numbers are, we're going to calculate slopes sometimes to get numbers like 50 or 100, really a slope of 3 in practice is already quite steep. Okay, so again, I want to contrast lines with non-lines. So the line case, the case where there's a slope, is the kind of benchmark that we're going to compare the other functions to. So can you tell when I was making up this example, I was staring sort of, slack-jawed at my coffee in the morning, watching the coffee come out and fill up the cup, fill up the carafe. And when the coffee is coming out, it comes out at a regular rate. I wrote down some made-up numbers there for how many cups in whatever time. But the idea is that it's coming out at a regular rate. So there's a point about what I mean by regular, and that is that if, for example, in the first minute you do the computation, you're looking at 1.5 and 1, you take a 1.5 minus 0, and 1 minus 0, so change in y over change in x. In this case, change in c over change in t, then you get a 1.5. It's just an elementary calculation. There you go. If, however, you take some different times, you get the same rate. So if you take 2 and 1.5, there's the change in c and there's the change in t. You get the same rate. So the point here is that a linear function such as the one I'm looking at here has a fixed rate of change. The change in c is the same no matter whether you measure that change between time 1 and time 0, or between time 1.5 and time 2, or between time 200 and time 319. You're always going to get a rate of 1.5. Now that, of course, contrasts with non-lines. Functions that don't graph as a line don't have a fixed rate of change. The sort of classic example is Galileo dropping the ball off the Leaning Tower of Pisa. So I got this goofy picture off the internet, and I used the formula for calculating the rate of change of a drop ball here, and I got these numbers from the formula. And I'm going to find the rate of change in various time spaces, and what's going to be important here is that it is not going to be the same from time to time. So for example, here I calculated between time 1 and time 0. And it's not a very interesting calculation, comes out to minus 4.9. Here I calculated between time 2 and time 1, and it's minus 14.7, but most importantly, it isn't 4.9. So it's not equal to negative 4.9 is the main point here. So the function's rate of change, a non-line function's rate of change, is not constant. What characterizes a line is that it has a constant rate of change, and we want to be able to work with non-lines. So if you wanted to actually calculate what's the ball's velocity, what would you do? So again, we're focusing on that same function that is, in some sense, the the height of the ball as Galileo dropped it off the Leaning Tower of Pisa, and I want to estimate it at some time. So I happen to pick time 2. Oops, made a little glitch there. I happen to pick time 2. I might estimate the velocity by taking the velocity between time 2 and time 2.1. So here we go. Delta y over delta x is time 2, time 2.1. The height at time 2 and the height of time 2.1, and time 2 and time 2.1. And again, I get some numbers. It's not really especially interesting what the numbers are. I get minus 20.09. All right, so I think that's 3 decimal places. So it's minus 20.090, I guess. Now that's an average velocity over time interval of 0.1 seconds. And you might say, well, that's a pretty good approximation. I can live with that. That's good enough for me. Fair enough, but we're going to make it better. So we might, for example, try to improve it by making the interval shorter. Instead of between time 2 and time 2.1, we're going to change it so we're looking at the difference between time 2 and time 2.01. Now, not surprisingly, we get a number that's not radically different than the number we just got here. The number we just got between the 0.1 seconds was minus 20.09. The number for the 0.01 seconds is minus 19.65, essentially. So it's not radically different, but it's a little different. And you might say to yourself, well, it's a better approximation because it's an average taken over a shorter time period. So in the sense that you're taking an average in both of these two cases, you're going to find that the ball is moving a little more slowly at the beginning of the time interval, a little faster at the end of the time interval. And so you'd think that, well, there's less time for that kind of change to happen in the second case. So we think probably the second average is a little more accurate than the first average. All right, so, we've done it a couple times. We can do it again. Here we go between time 2 and time 2.00001. And when you do the calculation, I didn't even bother to punch the numbers in. I didn't bother to show the numbers on the slides. You get minus 19.600049. And I think you must at this point feel that, really the velocity at time 2 is minus 19.6. Good enough. So what we've got then is we've got some sense of taking up these numbers over shorter and shorter time intervals and getting better and better approximations to the velocity. Okay, and that's what we're trying to motivate. This process of going shorter and shorter periods is we will call a limiting process, a process of taking a limit. I want to organize all this stuff into a table instead of a bunch of words and things slapped on the page. So I'm looking at the exact same formula, but I'm looking now at time 3, and there's the there's f of 3. Okay. And there's the 0.1, 0.01, 0.001. So as the time interval grows shorter, we see the change here is centering on some value. This is centered. This is around the anchor point 3 seconds instead of 2 from the previous slide. So here the time interval is growing shorter, but they're negative times, and still you see them. You see these numbers coming to some value, and surely I think a person who looks at this column, the change rate looks like it's coming to minus 29.4. So we would say the velocity of this ball at the instant time equals 3 is minus 29.4. The significance of the minus is that it's going down. Okay, let's see if I can hit the right buttons this time. There we go. Now, the function 58.4 minus 4.9x squared is, it's associated with the Galileo dropping the ball, so it's a perfectly reasonable function to look at. But the numbers are kind of awkward. So rather than do the awkward numbers, I'm going to make cleaner numbers by looking at the function f of x equals x squared. And again, I'm going to look around the neighborhood of a equals 3, just because the numbers come out better. And here's what I mean by that. That's a 3 and that's a 9. So it's easy to understand numbers. Exact same process though. I'm taking smaller and smaller delta x's. I could do the same thing in the negatives. And I'm finding that the delta y or delta x numbers are coming to some value. And again, exactly what we're doing today is motivating this process of finding that the numbers come to a value. And come on, a person's going to say, well, the answer is 6 here. So we're finding that these that this function at this point, the delta y over delta x comes to a value of 6. And I can look at other anchor points besides 3. Here I happen to look at anchor point that's negative, just to illustrate that you could look at negative anchor points. So if you plug in -2, of course, f of x equals x squared gives you a -4 for an output. And again, I'll save you, the sort of button punching to come up with these numbers in the table. But as the delta x's get smaller and smaller, that is to say, as we come to look at smaller and smaller intervals, we're finding that delta y over delta x is settling down at some value. And again, surely everybody thinks the value is -4. So we're touching on, we're motivating a reason for this process of why you would want to look at numbers that come closer and closer to either the 3 or the -2. And that process of coming closer and closer we'll call the limiting process. There's no reason why we have to focus on quadratics. We can look at sine of x, and so I happen to look here at y equals sine of x, and I happen to look at the anchor point of pi over 6. There's sine of pi over 6. And again, I have the delta x's coming to some value either from the plus or the minus side, and there's the delta y over delta x's, and again, coming to some value. And I think everybody's going to say, well, they're centering in on 0.866. The 3 decimal place is good enough. I could look at whatever functions you care to look at, but I happen to look at sine of x and also e to the x. So f of x equals e to the x, and near a equals 2, and there's a equals 2, and there's e to the 2. And again, the structure of the table is that the delta x's come down to be smaller and smaller, come down to be 0, and the delta y or delta x's settle on some value. I think a person would say that something like 7.390 or 7.389 or something in there. Okay, so we're finding that as the delta x's approach 0, for this function at this anchor point, the delta y over delta x's approach some value. I want to start asking about why what's that value? Why is that particular number? And so I want to ask about a particular example, just because I like things to be concrete. And so I'm going to focus here on the example that we looked at earlier, f of x equals x squared. And I'm going to focus on a equals 3. It's centered around a equals 3. Same table, there's delta y's, or at least much the same table. Delta x is going to 0, and here's the 3 and the f of 3. And I don't have a delta y or a delta x. Instead, I wrote it just as simply as delta y, and I think what a person can see, I think this makes it a little clearer, what a person can see is that it's getting to be the case that the delta y's are 6 times the delta x's, and the delta y's here, the delta y's are 6 times the delta x's, both the positive and negative direction. So restated, near to a equals 3, the input-output relationship is x goes to x squared is approximately x plus delta x goes to 9 plus 6 delta x. So why is that? What's the 6? Why are we coming up with a delta y over delta x of 6? What's the explanation? And the explanation is, it's not just a question of punching some numbers and that's what shows up in the table. You can actually understand it on a sort of logical level. So fine, we took f of 3 plus delta x squared, and multiplied it out, and there you see 9 plus 6 delta x plus delta x quantity squared. So there's a 6 there. All right, so why does that 6 turn out to be important? So again, I organized the table a little bit differently just to try to present the information that I have. You see here where it says 9 plus 6 delta x plus delta x squared. So I wrote the 6 delta x and the delta x squared, and I'm trying to focus on those numbers. It's a big table, and there's a whole lot of numbers, but I want to focus on this line right here, the 0.001 line. There we go. If I can draw straight through it. There we go. Oh, not bad at all. I think what you see, the delta x the delta x of 0.01, and the delta y is 0.006001, 0.006001, and that number is made pretty much almost entirely of the 006. The 0.00001, it's true, it's there, but it's orders of magnitude smaller than the 006. That is to say, of these two parts, double-ended arrow there, of these two parts, the linear part, the part where delta x to the 1 power, not delta x to the 2 power, the linear part is by far the much more important one. So when you consider the change near A, what matters most is the linear component of the change. We are interested in the rate of growth, and the rate of growth is dominated by the linear growth near to A. I just want to do another example just to show that I didn't, I didn't pluck an example that's really a bit of a lie. So I chose f of x equals x cubed, and I chose a equals 2. So there's 2 and 2 cubed. Okay, and again, we're going to see a phenomenon. So again, I'm going to focus in on this line, the 001 line here, and also down at the bottom in just a second. So focusing in on that 001 line, I think what we're seeing is that if x is 001, then delta y over delta x is 12 point something. So something like here, we're focused in, we're close to 12. That what a person would write in here is something like 12. Okay, where'd the 12 come from? What's this about 12? What's this all about? So I did the same thing on the prior slide. I expanded the cube. This might be a little less familiar than expanding a square, but anyway, I expanded the cubed, and I got 12 delta x there. I made a 12 delta x column, 6 delta x squared, there's that column, and the delta x cubed, there's the delta x cubed column, and I got my computer to print out all these numbers. And again, I want to focus on the 001 line just to focus on something. Oh, it's so hard to draw a straight line on this thing. There we go. There we go. Focus on the 001 line. And I think what a person sees is that of the columns, of the linear column, the quadratic column, and the cubic column, surely the linear column is the one that matters. 012, this is 00006. This is, how many O's are there? So 3, 6. We're on 10 to the minus 9 here. So of the three columns, it's the linear column that by far dominates the change. That if we focus on the change implied by the linear column, we're focusing mostly on what matters. The higher order changes here, higher order changes are very much smaller than the first order change. Okay, so we have this sense, we're motivating this sense that what we want to do to understand how functions change is that we want to somehow look at this process of saying what happens near to a equals 2, or what happens near to a equals 3, or what happens near to a equals minus 2, and understand how the function changes in the neighborhood of 3 or 2 or minus 2, because these functions change at different rates in different places. Okay, now next set of slides we'll talk about that. We'll give it a strict definition of that, a formal definition of that. Before we go there, though, I want to spend just a few minutes thinking about 3 ways to think about the rate of change. In this course, we're going to talk about rate of change a real lot, and I want to start off by thinking about the 3 main ways we're going to think about the rate of change. The first way here talks about the Galileo dropping the ball off the Leaning Tower of Pisa, and the ball was falling at a certain rate after 1 second, and a different rate after 2 seconds, and a still different rate after 3 seconds. That is to say, the velocity of an object whose position is given by the function is one way to think of rate of change. Rate of change, you have an object whose position is given by some function, and I gave the function for the ball that Galileo dropped, and the rate of change of that position is the velocity. So we've seen here that for f of x equals x squared at a equals 3, the rate of change is 6. If this person's position at time t is t squared, Then at time, whoops, t squared. Then at time 3, this person is moving at a velocity of 6, positive 6. Moving at a velocity of 6. P of t, there we go, P of t is t squared. So one way to think about that is driving along in a car, you look down at the speedometer, and what you're doing is watching the car's rate of change of position. You're watching the car's velocity, you're watching the car's rate of change of position. Okay, so in fact, rate of change of position is familiar because we've all looked down at speedometers. Second way to think about the rate of change of a function. So in the tables, I showed a half dozen tables. In the tables, when we find the rate of change expressions, we're always calculating here, when we calculate delta y over delta x, we're calculating f of a plus delta x minus f of a over a plus delta x minus a. And that's the slope of a line. That's the slope of the line between a comma f of a, you see it here, and a plus delta x, f of a plus delta x. You see it there. Can you see down at the bottom? I have a and a plus delta x. So this line, this red line right here. This red line is the number that we calculate as delta y over delta x. That's called a secant line. Crosses the blue curve in 2 spots. If I slide delta x to be smaller, as I did in the tables, if I slide delta x to be smaller, then what's happening is that secant line is approaching. That secant line here is approaching a tangent line. You can see why I do slides. My handwriting is so bad, and it's also the tablet doesn't help. So the fact is that as x gets near to a, said another way, as delta x gets near to 0, oops, went too far. As x gets near to a, so that delta x is getting near to 0, the secant line is approaching a tangent line. Now, if we let x equal a, then the delta y over delta x has a denominator of 0, so that fraction doesn't make any sense. But if we think about the table numbers for f of x equals x squared near the anchor point a equals 3, we say that it makes intuitive sense to say that the slope is 6. So we'll say that this line here is slope of 6. And of course, we'll give formal definitions for how you can make sense of all those things next time and in upcoming classes. But the idea is that when you look exactly at delta x equals 0, you get a problematic expression. But if you take somehow the trend, the tendency, as delta x gets close to 0, it's perfectly clear that the answer is 6. And then the third way to think about the rate of change, probably the most abstract. We usually picture functions on an xy coordinate. So we would draw an x and we'd get some function like so. But sometimes we're going to want to, in this class, draw the two axes parallel. So this is the x-axis and this is the y-axis. And here I've drawn f of x equals x squared. You can see, for example, that you can see here that 4 is mapping to 16. 3 is mapping to 9, 2 is mapping to 4, etc. Okay, so what does that have to say? And the answer is that each input interval maps to an output interval. So for example, if you take the interval from 3 minus 0.1 to 3 plus 1, then that interval will map to an output interval of 9 minus 0.59. I just did it on a calculator, that's all. 9 minus 0.59 to 9 plus 0.61. Input intervals map to output intervals. So the one that's pictured here is 3 plus and minus 0.4 maps here to the output interval 9 minus 2.24 and 9 plus 2.56. I couldn't make the interval too small, otherwise the circles overlapped. If I focus again at the anchor point 3 and its associated output 9, and I let the delta x's go to 0, the delta x's go to 0 both from the positive and negative direction, then what we're seeing, of course, is that the output is about 6 times. The output is about 6 times, here we go, about 6 times the input, so we're looking here at a 6. That is to say that in moving from the left-hand side to the right-hand side, in the neighborhood of x equals 3, intervals grow to be 6 times as big. Again, said again. In moving from the left-hand side of this picture, from the x's, to the right-hand side of this picture, to the y's, intervals grow to be 6 times as big. And you see that up here. This interval grows to be about 6 times as big. So the table shows that near the anchor point a equals 3, this function transforms small input intervals to output intervals that are about 6 times as long. So the function's rate of growth, a third way to understand rate of growth is that the function's rate of growth is its local scaling factor. Okay, so next time then we're going to start in on we'll give the definition of limit, this process of trend or tendency, and then we'll start in, that will be the first day we have homework, go through some homework, that kind of stuff. Okay, so very good, look forward to that, see you then.